Okay, welcome. I appreciate you all coming to the session today. And I will warn you in advance, I am in the unenviable position of presenting my doctoral students' work. So all the detailed questions that he would be able to answer were he here will fall upon me. So when I fail in that regard, I apologize. So what I'm going to speak about today is some work that we were doing in Kentucky on modeling differential bridge settlement, or as it's more commonly described, the bump at the end of the bridge. So the nice thing about studying a topic like this is when I explain to my wife or somebody outside of the field, you know, what kind of research project you're studying, oftentimes you have to go through this level of explanation to try to get down to it. And this one's basically, you know, when you're driving along the road and you come up to a bridge and there's a bump that jars your car. That's what we're studying. This is one of the most widely studied topics in the field of civil engineering. And the reason it's a problem, other than just being annoying when you hit that bump, is that it's a safety issue to motorists, particularly motorcycles. If the bump gets too severe, it can damage the vehicles and the bridge structure itself as you have repeated heavy loads battering on that bridge abutment. It has maintenance cost and you know, the universal sign of construction work, the orange barrel, orange marker that's shutting down lanes as it is repaired. There are many factors that can contribute to the bump at the end of the bridge, and so there's a few listed here that you'd be familiar with, but ultimately the problem comes down to you have a very rigid, inelastic structure right next to an elastic material, the bridge embankment there. And whether that's soil or water that's coming through that starts to cause that movement, it's something that you know, can occur. So the objectives for what we were looking at this is to identify the factors that influence bridge settlement. And honestly, that's pretty simple because it's been studied so much you can get that with a literature review. And then what we really wanted to do was develop a model to help predict risk for this. And our ultimate goal was to develop a tool that could be used during the project planning phases and throughout the project execution phase to analyze this settlement risk. Much of the work done in this area looks at developing solutions for the bridge bump. So putting geotechnical fabric in the approach abutments, putting approach slabs as you come up to the bridge. Those have been studied quite a bit. What we wanted to look at is at a very macro level, look at these multi-contributing factors, and so that the state could go in and say, we're building a new bridge or we're modifying a bridge in an area. What is the risk, what level of risk is posed with this bridge bump as we go through this? So what we began to do was go through a very large data collection effort to get inputs into this model. Many of these are pretty straightforward and seem simple, but when you go try to actually find what they are, what the data is, it starts to become very complex. And so, you know, basic information, length, width of bridges, those are maintained within existing databases. You can find the bridge number, you can find out that type of information. When you're starting to look at approach types, approach age, now you're going back to the original design drawings for the bridge itself to start to pull that information out. So Dr. Zhang, who worked on this, got to sit on a computer and comb through bridge plans from the 60s for Kentucky. We'll see the data set here in a moment, to identify most of those by hand. Embankment material, so what we use to fill to bridge up to the bridge abutment, it's nearly impossible to identify what that is unless you go out and drill a hole, because it's whatever they had available there. They had what they were supposed to put in there. That might have been what got put in there. It might have not been. And then characteristics for the foundation soil. So the foundation soil for the approach there, what type is it, how deep is it? And then finally the transportation district. U.S. state DOTs are often organized in regions. There's 12 districts in Kentucky. That's a very useful method to, you know, approximate many other variables as using the district. So if I asked you to define settlement, probably everybody in here would be able to define it as a measure how far did something sink in centimeters or inches. And so how do you measure it? Well, you can go out there and stick a ruler in the ground and at the end of the bridge and see how much it's settled. But when you're actually trying to get that information, it's very challenging because the state DOT doesn't collect that type of information. They collect data on bridge repairs. They collect data on visual inspections, but there's no measurement that says this bridge is settled 1 inch or 2 inches. And then furthermore, if they had that measurement, you wouldn't know really how critical that is unless you understood, well, it's settled 1 inch and we fixed it 6 months ago. Or it's settled 1 inch and the bridge was built 6 years ago and we've never had to do any repairs to it. So we also thought about looking at, well, what about the tons of asphalt that you use to fix this? Typically the way you fix these problems is you go in and install a layer of asphalt. They don't track that explicitly to the bridge. It's just tracked. We put tons of asphalt in this region and you don't really know necessarily what it's for. So what we focused on looking at ultimately was the repair frequency. If this is a problem bridge, they're probably going to be in there fixing it more often. If it's not a problem bridge, you're not going to be fixing it. And the way we were able to track that is we went through 2 different methods. We had an inspection history where every year or 2 years, depending on the bridge type in Kentucky, they have to inspect the bridge and they would rate the condition of the approach on a 1, 2, and 3 scale. So if it's in bad shape and then suddenly it's in good shape the next time it's inspected, it's probably been repaired there. The other thing that we did was we did a survey amongst district personnel to identify, well, what's your problem bridge bumps? Because they're the ones that are dealing with having to fix them. And so we can see what's coming out in the database of the maintenance inspection records, and that's a valuable tool for us. But you also have the information of the people who are managing the bridge and saying, yeah, this one bridge is a pain in the butt. Every year we have to go in and wedge this, or every 6 months. And so we were able to build 2 different data sets, to construct 2 different models from this. And I'm going to go quickly through the regression method we used to build the model, because I think the interesting part of this work is the tool you end up developing to use it. So what we ended up using with this type of data, since we had the numerical and the categorical data, and we weren't necessarily looking at predicting an exact value. We were not going to predict that the bridge is going to settle 2.3 inches. We were going to predict, is it going to be frequent repair, less frequent repair, or somewhere in the middle. And so we ended up using ordinal logistical regression and multinomial logistical regression. The difference between those two is that whereas regular linear regression that we're usually familiar with predicts a value, 2.2 inches, whatever. This one predicts a range, a percent probability of several different states. And I'll show you an example here in a moment. And the difference between them has to do with how dependent are the different end states upon one another, basically. So go through, we had this massive data collection effort, used our statistical software, and then we created 2 different models. We had a model, the first model, that was based on the perceptions of the state DOT people. So you ask them, what are your problem bridges? They tell you. What are your good bridges? They tell you. So we're able to build some information off of that. So for this model, we ended up using the multinomial model, what ended up being recommended. For the second data set, which was the larger data set with the 600 or so bridges based on maintenance history, for that one, both methods returned a very similar result when you analyzed the data and looked at doing it. So, one of our objectives was to look at what are the factors that influence differential bridge settlement in Kentucky. Well, if you look at the major critical factors that we saw coming out of both these models, age of approach is common between them. The district or the geographic region is common between them. And then the foundation soil depth showed up in the survey model versus did not show up in sort of the larger maintenance record database model. Approach type showed up in the PONUS database model. And, one of the things that was interesting, one of the methods to combat this problem is to install what they call a sleeper slab. So basically, instead of placing asphalt all the way up to the bridge approach and having just compacted soil underneath it, they would put a reinforced concrete slab under up to the bridge abutment under the roadway and then put the asphalt on top of it. And when we met with the different districts and we asked them about this approach, roughly half of them said, yes, that's a very useful way to address this problem. It kind of makes the problem go away. The others said, well, it does remove the bump from the end of the bridge, but it ends up making a bump in the road now because you still have that differential settlement. It just occurs at a different place. The other issue that came up was that with that slab, if you had the road being eaten out because you had water drainage problems or something like that, you ended up with a void space. That reinforced slab would hide that for a long time. And then when it failed, it really failed, and it was a lot more expensive to fix. So there was some folks that, you know, in their professional opinion, it was a great solution to use. There were others that it was not as much. So these were our major factors. So moving forward, what we were looking at doing was saying, okay, the upper model is the model from sample 1, the lower model is from sample 2, and so you get this big ugly regression equation. How do you use it to do something useful with? So what we did was we took the regression equation and made a pretty simple Excel sheet to contain the information. It's got a macro. You pick which model you want to use depending upon what kind of results you're wanting to look at. And it's got various inputs for you know, the district, all the different factors that I listed there. And so you can input those, and when you input them, it gives you a readout, which I will pull up here. And so you basically have 3 different settlement risks: minimal, moderate, and severe. And what these regression equations do for you is they give you sort of a percent probability that you're going to have one of these conditions. So for this example here, based upon these conditions that I put in for this sample, you have an 88%, you know, it predicts the 88% chance that you're going to have a moderate settlement. So, you know, that's an effective tool, at least implementing those, you know, ugly looking equations there. But how do you actually use the tool to do something useful? Well, if you take a look at the development process for state transportation agencies, particularly in the United States, it's the very traditional design, bid, build approach. And so you go through the planning phase, the design phase, operating it and maintaining it. They're very much in most DOTs. I'm talking about Kentucky because that's what the project that we were on, but in most DOTs they are extremely siloed. There's not a lot of communication between the two. So if you have a tool that predicts how much settlement you're going to have based upon your bridge design, who should be analyzing that tool? Who should be using that tool? Okay, well, it should be the bridge designers because they're the ones that are designing the bridge, and they maybe have some approaches that they could potentially change. The tool goes through based on some best practices that we grab that says, for these factors you should consider, you know, these types of remediation methods. Does a bridge designer really care about the bump at the end of the bridge? No. If you talk to bridge designers, they're sort of incredulous that you dare connect a road to their bridge. And furthermore, that's a maintenance problem. That's not a bridge design problem. That's something that's, you know, 5-10 years down the road. So maybe you give it to the road designer. Well, if the road designer uses it, once again, you're kind of in that same situation of, do they really care if it settles or not? So it can be used to inform design. Should it be the construction folks, the pre-project planning that use it? There's certainly many factors in construction that can come in and influence this, particularly with the compaction of the fill material. And you can really see that when you have a deep fill. If they put the fill in and allow it to settle for a year or so before they put the road on there, you can have an influence on that. And so ultimately, should it be the maintenance people that are using it? The maintenance people don't have any control over the design, but they are the ones that are having to deal with the settlement, fixing the problem. And so when, if they're using it, they can't influence design, but how can they end up using it? So what we're currently working with the cabinet on is, who is going to own this tool? And the current idea that we're working through the implementation on is that it would be something that would be looked at in the bridge design. And, the important part of that is just because this tool tells you that your design is going to produce severe settlement, that doesn't mean you need to go change the design, because it could be that the design is that way for a specific need, and the fact that this thing's going to settle is something that you're just going to have to live with. Ultimately, I think where it's going to end up falling is they'll probably, this is my guess, they'll give it to the bridge people, and the bridge people will fill it out because they say they have to fill it out and turn them in with their final bridge plans, but it's ultimately not really going to inform anything. The maintenance people are pretty interested in it from the standpoint of using it as a tool to help them budget and plan for future maintenance activities, that if you have a bridge that's going in or being repaired, that you can start to use that to plan that, okay, we're 3 new bridges and we're gonna have to be focusing on them because of the settlement prediction. So I appreciate the time. I know we kind of skimmed over quite a bit of that. I would be happy to answer any questions you may have.